So because of the associations between the molecules, it always decreases the number of particles. So why our hands and the legs will be swell when you do too much of work on the water? Because of the osmosis. Especially from the animals and also from the vegetable region, we can prepare the semi-permeable membrane. Hello my dear students, a warm welcome you all. Myself is Purnima, lecturer in Department of Chemistry at Vidhyaashram Pre-University College, Temple of Excellence, Mysuru. My dear students, in our last discussion, we were dealing with the unit called solutions. Under that, we were dealing with the colligative property. So what is colligative properties? Colligative properties are the property which depends only on the number of solute particle. Instead of their nature, it depends only on their number of solute particle which is found in the solution. And also in the colligative property, we have studied about the three main colligative property. Which are those? First one is a relative layering of vapor pressure, then elevation in boiling point and depression in freezing point. So these three derivation, it is very important for the examination point of view, and also to solve the numerical, the final equation will be very important. Today we'll move on to the last colligative property, that is osmosis. We'll see what is osmosis and we'll discuss the osmosis in the natural processes. And what is osmotic pressure? We will discuss. And also we are going to discuss about the reverse osmosis and abnormal molar masses and Vanta factors and its numerical. So let's begin the session by knowing what is osmosis. So we all familiar in our lower classes, we have studied about the osmosis, right? So can you quickly recall it? What is the osmosis? Osmosis means it is nothing but a spontaneous movement of the solvent molecule from a lower concentration region to the higher concentration region. So this is a picture which actually shows that how the osmosis will be taking place. It is nothing but a movement of solvent molecule from a lower concentration region to the higher concentration region through this semi-permeable membrane. Through the semi-permeable membrane, it is known as osmosis, right? So we learnt about the osmosis and also we have learnt about the diffusion in our lower classes. So what is osmosis? It is nothing but a spontaneous movement of a solution from a lower concentration region to the higher concentration region through a semi-permeable membrane. So what is osmosis? It is nothing but a flow of solvent molecule from a lower concentration region to the higher concentration region through a semi-permeable membrane. What does this semi-permeable membrane means? So it is nothing but a membrane which allows only the solvent molecules to move from a lower concentration region to the higher concentration region. Remember, it will select only the solvent molecule but not for the solute molecule. So it is specially meant only for the solvent molecules to pass from the lower concentration region to the higher concentration region. Hence, it is known as semi-permeable membrane. Remember, this membrane can be obtained from the natural as well as from the synthetic origin, especially from the animals and also from the vegetable region, we can prepare the semi-permeable membrane. Example for the semi-permeable membranes are cellophane, parchment paper and pig's bladder. So these are the few examples for the semi-permeable membrane where it allows the passage of solvent molecules but not to the solute molecules to pass from the lower concentration region to the higher concentration region. Hope you all understood with the definitions of the osmosis. Now, we'll see, so which role the osmosis process which also takes place in our daily life. The best example I can give you is during the preparations of the pickle. What we used to do? We used to keep the raw mango in the high concentrations of the salt, right? So why we used to keep the raw mango in the high concentrations of the salt solution? Only to remove the water content in the mango. So why we need to keep the raw mango in the high concentration of the salts? In order to preserve for the longer time. If you want to preserve the food for the longer time, we usually have a habit of preserving the food with the high salt concentration, either with the high sugar concentration. During the preparations of the pickle, usually the vegetables or with the raw mango, they used to keep in the high concentrations of the salt, so that water content which is there in the raw mango or in the vegetables, it will completely removed, so that we can preserve it for the longer time. So during that preservation processes, the water content will be removed because of the high concentrations of the salt which will be placed in the raw material. So there will be osmosis will be taking place from a lower concentration to the higher concentration region. That is why it is a best examples for the osmosis. And another example is, in our daily life also, once we pluck the flowers from the plants, what we used to do? We used to keep it in a fresh water. Why we used to keep? In order to keep it for the longer time. For the next day also, we used to keep it in a water. Especially the wilted flowers will be revived when it is placed in a fresh water. So whatever the flowers you pluck from the plant body, we used to keep it in a fresh water just to preserve for the another day. So during that preservation, remember, again the osmosis will be taking place. And next, the people who took a lot of salt or a salty food, they may experience with the retentions of the water content in the cell and also intercellular space because of the osmosis. So this is usually resulting in fluffiness or swelling, that is also known as edema. You would have seen with a few people, if they took too much of salty food, they may experience that when they sit in the seats or in the buses, the entire seat will become very wet. Have you all observed? Yes, because of the osmosis. So these are all the examples for the osmosis which also taking place in our daily life. In addition to this, we all know that, especially green plant, what it will do, in order to get the water from the roots, it will plug the water mainly from the root, or it will suck the water mainly from the root. So during the sucking, the water has to be transported from the lower concentration region to the higher concentration region. So that is another examples for the osmosis which also taking place in a green plant. Another best example is, during the preservations of the meat and also the preservations of any food, we used to keep it in a high salt content, either in a higher sugar content also. Why we used to keep it in? Because in order to avoid the bacterial growth. We all know that if you keep the food for the longer time, it will be spoiled by the bacteria and also by the fungi, right? In order to avoid this bacterial growth, we used to have a habit of keeping the food content, especially in the high salt content, either in the high sugar content. This high salt content or the high sugar content, it will remove or it will avoid the bacterial growth, because the bacteria which is having a water in their body, so their entire water will be removed when it is placed in a high salt content. That is why the bacterial growth cannot be easily observed when you keep the food in a high salt concentration. In addition to this, I can give you another example. For example, imagine you're doing some work in the water. If you do the work longer time in a water, your hands and your entire body, if you see that, especially the hands and the legs, it will swell. So why our hands and the legs will be swell when you do too much of work on the water? Because of the osmosis. Because our body itself, the skin itself will be act as a semi-permeable membrane. It allow the water inside our body. That is why after doing so much of work, our entire legs and hands, it will swell because of the osmosis. So these are all the examples for the osmosis which also taking place in our daily life. Coming into the osmotic pressure. We all know that osmosis, which is nothing but a movement of a solvent molecule from a lower concentration region to the higher concentration region through this semi-permeable membrane, right? So if you don't want to continue this osmosis, what I'll do, I'll apply some pressure to this solution which consists of higher concentration. Okay, so that pressure itself, which is known as osmotic pressure, osmotic pressure. Okay, so let's see with the definition. So what is osmotic pressure? We all know that during the osmosis, the flow of solvent molecule from the solution of lower concentration into the solution of higher concentration of a solute through a semi-permeable membrane will be taking place, right? So during the osmosis, what it will do? So the solvent molecule from the lower concentration region to the higher concentration region, it will move through a semi-permeable membrane. So that is known as osmosis. So if you wanted to stop the osmosis, what you will do? You will apply some pressure, especially to the solution which consists of higher concentration, right? So that is said to be osmotic pressure, which is known as osmotic pressure. So we'll see with a simple definition. Osmotic pressure of a solution, it is defined as the pressure is applied on the solution of higher concentration just to stop the osmosis. In order to stop the osmosis, we will apply some pressure on the solution which consists of higher concentration, right? So that is said to be osmotic pressure. And this osmotic pressure, remember, it is a colligative property. Why it is known as colligative property? Because it depends upon the number of solute particle instead of their nature. So that is why the osmotic pressure, it is also known as colligative property, because it depends only on the number of moles of the solute instead of their nature. So we'll see with the derivation. We all know that the osmotic pressure, it is nothing but a pressure which is applied on the solution just to stop the osmosis. We also know that for a dilute solution, it is experimentally proved that osmotic pressure will be directly proportional to the molarity, which is proportional to the molarity, right? So I can write osmotic pressure which is directly proportional to the C. That is nothing but a molarity. In order to remove this proportionality constant, I can place, that is osmotic pressure, which is equal to K into C, where K is a proportionality constant. Remember, C is a molarity, because for the dilute solution, osmotic pressure is directly proportional to the molarity. And also, here the proportionality constant can be also written as RT. Here, K is nothing but a RT. R is a gas constant and T is a absolute temperature, which is expressed in terms of Kelvin. So, up to here, I hope you all understood with the derivation. Now, I can write osmotic pressure, which is equal to CRT, where C is a molarity, R is a gas constant and T is a temperature. In order to calculate the NB moles of solute dissolved in V liters of the solution. That is, what does the molarity says? Molarity, which is nothing but a number of solute which is present in a solution divided by total volume of the solution, right? So that is why I can write C as NB divided by V. NB is nothing but a number of moles of the solute divided by total volume of the solution, that is V. So if you substitute the values of the C in this equation, you will get osmotic pressure which is equal to NB divided by V into RT. Okay? We all know that NB is nothing but a number of solute particle. So from the mole fraction, we also understood that how to calculate the number of moles. How do we calculate the number of moles of the solute? It can be obtained by mass of the solute divided by molecular mass of the solute, right? So mass of the solute divided by molecular mass of the solute, which gives rise to the number of moles of the solute. So I can write NB as WB divided by MB, so that Instead of that, I'll write directly, that is WB divided by MV into RT divided by V. Now, in order to calculate the molar mass of the solute, that is a MB, molar mass of the solute. So, I'll take out the MB outside so that the pi will come here, that is nothing but osmotic pressure. So, that MB is equal to WB into RT divided by osmotic pressure into volume. Remember, WB is nothing but a mass of the solute B, and R is a gas constant, T is a temperature, V is the total volume of the solution, and pi is nothing but a osmotic pressure. So, this is how the molar mass of the solute can be calculated by using this osmotic pressure equation, as we obtain in case of elevation in boiling point, depression in freezing point, and also in the relative lowering of vapor pressure. Like this in osmotic pressure also, we can calculate the number of moles. This is a molecular mass of the solute. Understood? So, this is a final equation to calculate the molar mass of the solute by using the osmotic pressure equation. Hope you all understood. We'll move on to the next topic, that is types of solution in the osmosis. So, usually we have three different types of solution we can express. First one is isotonic solution, hypertonic solution, and hypotonic solution. So, especially for the 2 marks, from this part, they are going to ask at least one question. What is isotonic? What is hypertonic? Or what is hypotonic solution? Give an example. It is very important for the examination point of view. Let's see what is isotonic solution. If two solutions having same osmotic pressure at a given temperature, then we say it is a isotonic solution. Best example is the red blood cells is an isotonic with 0.9% of NaCl solution, which is known as normal saline, which is used in injection instead of distilled water. So, if you see this picture, you can clearly understand that this is an example for the red blood cells, which is kept in an saline solution, that is normal saline solution. So, this is a red blood cells which has been kept in normal saline solution, that is nothing but a 0.9% of sodium chloride. 0.9% of sodium chloride. So, if you keep this red blood cells in a normal saline solution, in these two solutions, there will be no osmosis will be taking place. Why no osmosis will be taking place? Because in these two solutions, remember, the osmotic pressure will be same. Such solutions are called as isotonic solution. The pressure in the RBC, that is in red blood cells, and also the pressure in the saline solution, that is in NaCl, both are same. That is why in an isotonic solution, the osmotic pressure will be almost equal, so that there will be no osmosis will be taking place. Such solutions are called as isotonic solution. Remember, isotonic solutions are the two solutions which are having equal osmotic pressure. Okay, they are said to be isotonic solution. The best example is if you keep the red blood cells in a normal 0.9% of sodium chloride solution, that is nothing but a saline solution. In this solution, there will be no osmosis. Why not? There is no osmosis because in these two solutions, that is in the red blood cells and also in the saline solution, osmotic pressures are almost equal. Because of the osmotic pressure is equal, there will be no movement of the solvent and the solute will be taking place. That is why it is known as no osmosis will be taking place in case of isotonic solution. Hope you all understood with the isotonic. We will move on to the hypertonic solution. The solution whose osmotic pressure is higher than that of the given solution. So, the solution in which the osmotic pressure will be higher than that of the given solution, it is known as hypertonic solution, which is known as hypertonic solution. When RBC is placed in seawater, the water will be passes out of the cells due to osmosis and cell will be shrinks. Here there is a example for the hypertonic solution. So here again I am keeping the red blood cells in an seawater. In an seawater, we know that in the seawater, what it is there? It consists of higher concentrations of the salt. So due to the higher concentrations of the salt, you know, the water which is present in the red blood cells will be start moving towards the salt water. So what happens if the water is completely removed from the red blood cells? So that red blood cells will be shrinks. So it will shrink so that it will remove the water because of the osmosis. Why the water is removed? Because of the osmosis. We know that from the osmosis, the water or the solvent molecules always it move from lower concentration region to the higher concentration region. Because you are considering the red blood cells which has been placed in a higher concentrations of the seawater. That is why the red blood cells will undergo shrinkage because of the water has been removed from the red blood cells and it will pass towards the high salt concentrations of the sea because of the osmosis. So such solutions are called as hypertonic solutions. So what is hypertonic solution? It is a solution in which one of the osmotic pressure of the solutions will be higher than that of the another one. So which is known as hypertonic solution. The best example is red blood cells which has been placed in an seawater. The seawater which consists of what? High concentrations of the salt. Due to the high concentrations of the salt which is there outside the red blood cells, you know, the red blood cells which consists of the water molecule, it will be start moving towards this seawater so that there is a osmosis will be taking place from the lower concentration region to the higher concentration region. So at finally red blood cells will be undergo shrinkage. So this is an example for the hypertonic solution. Next we'll move on to the hypotonic solution. The solution whose osmotic pressure which is always lower than that of the given solution. So that it is known as hypotonic solution. Example, when RBC is placed in an hypotonic solution, they will swell and even it will burst due to the inflow of water due to the osmosis. So here the hypotonic solution which I have placed the examples of the red blood cells whose concentrations will be lower than that of the solution, given solution. Such solutions are called as hypotonic solution. Here I have placed the red blood cells in a solution whose concentrations will be lower. So what will happen? Obviously, the water will be started move towards the red blood cells so that red blood cells will occupy some more water and it will bulge. Okay, it will increase its size because the water has been coming from the outside because of the inflow of water, and this is because of the osmosis. You know, the water from the outermost portion, it has been moving towards the red blood cells so that red blood cells will be increases in volume and it will get bulged. So this is an example for the hypotonic solution. Hope you all understood with the hypotonic, hypertonic and isotonic solution. It is very, very important for the examination point of view. Okay, one example along with the definition you should remember. Next we'll move on to the reverse osmosis. We all know that what is the osmosis, right? So what is the osmosis? It is nothing but a movement of solvent molecule from a lower concentration region to the higher concentration region through a semi-permeable membrane. And also to stop the osmosis, we have applied some pressure mainly onto the solution which consists of higher concentrations of the solution, right? So that is said to be a osmotic pressure. Here, remember, reverse osmosis means it is a process of reversing the directions of the osmosis by applying the extra pressure to the solutions of higher concentration. That is said to be reverse osmosis, which is nothing but a what? So we know that generally in the osmosis, what will happen? The solvent molecules will be moved from lower concentration towards the higher concentration region. Here the solvent molecules will be moved like this through a semi-permeable membrane, right? But the reverse osmosis means the movement of the reverse directions of the osmosis. The movement of the solvent from a higher concentration region to the lower concentration. For this, they will give a extra pressure. They will apply a extra pressure so that reverse osmosis will be taking place. The reverse directions of the osmosis will be taking place because of the extra pressure which is applied on the high concentrations of the solution. Hence, it is said to be reverse osmosis. Where we will use this reverse osmosis? So, reverse osmosis will be mainly used in the desalinations of the water. Desalinations of the seawater, during that process, we use the reverse osmosis. Remember, during this process, when the pressure is more than that of the osmotic pressure is applied to the seawater and the pure water will be squeezed out and the seawater through the semi-permeable membrane. So, during the salinations of the seawater, they will follow the reverse osmosis. What does the reverse osmosis means? Reverse directions of the osmosis, okay? Where the solvent molecule will be moved from higher concentration region to the lower concentration region. Why it is moving in a reverse direction? Because you are applying more pressure than the osmotic pressure. Okay, so that is said to be reverse osmosis. That is why I have mentioned here. During the reverse osmosis, pure solvent will be flow out of the solution through a semi-permeable membrane. Understood? And remember, this process will be mainly used in the desalinations of the sea water. So again, this is also important for the examination point of view. For the 2 marks, they can ask you what is a reverse osmosis. Okay, where we will use the reverse osmosis. And the variety of the membrane can also use for this purposes, which are mainly the cellulose triacetate and also the thin film composite, that is the TFC membrane, can be used for this purposes because it has to be withstand the higher pressure of the movement of the solvent molecule from the higher concentration region to the lower concentration region. That is why they will use a different membrane for this processes. Hope you all understood with this topic. Next, we'll move on to the another different topics of this unit, that is abnormal molar masses. As we already know that from the qualitative property, we can easily calculate the molar masses of the solute. But as we obtain the molar masses of the solute, it may be higher or greater than the normal value as we calculated by using that qualitative property. So, due to this variations in the values, then we say it is a, if it is there, then we say it is a abnormal molar masses. Let's see what is that actually. The molar masses of the solute can be calculated by measuring any one of the qualitative properties of the dilute solution, right? So, we used to do a calculations on the molar mass of the solute by considering any one of the qualitative property. But actually, it is applicable only to a dilute solution where it obeys the Rolle's law, right? And also, if it does not obey the Rolle's law, remember the solid will be undergo associations or the dissociation processes. So, that is known as abnormal molar masses. Or in a simple words, I can say that the molar mass of the solute can be calculated by using any one of the qualitative property. But actually what we calculated, the value we obtained, that never suits for the normal value. There is a lot of variations will be taking place. So, that is known as abnormal molar masses. Okay. So, why the abnormal molar mass will be taking place? Because of the associations or the dissociations of the ions. We'll see what is the association molar masses and dissociation molar. So, the association of the solid molecule, it is mainly due to the certain solute in a solution are found to be associated. In such cases, what will happen? This lead to the decrease in the number of molecular particles in a solution. Certain solutes in a solution, remember, it is found to be associated. It goes to be combined. It will get combined. Okay. So due to the association, what will happen? The total number of molecular particles will be get reduced. If it is get reduced, remember, the result should be decreased and results in a decreasing in a colligative property. So that is why the molecular mass of the solute will be proportional to the 1 by colligative property. The best example I can give you is acetic acid. The acetic acid in the benzene solution, it will undergo dimerization. Which will undergo dimerization. Why it will undergo dimerization means because of the associations of the solute molecule. So the acetic acid, so here this is a 1 mole of the acetic acid, CH3COOH, right? So 1 mole of the acetic acid or the one acetic acid molecule, it will combine with another acetic acid molecule and it undergo dimerization. So one acetic acid will be behave like a 2 acetic acid molecule. So this is mainly because of the associations of the solute molecule or the solute. So if the association which is taking place, remember, there is always decreasing in the colligative property value. So this is known as associations of the solute molecule because of the dimerization. Next we'll move on to the dissociations of the solute molecule. What does this dissociation means? In certain solute in a solution which is found to be dissociated into ion. The best example is sodium chloride. If you take the sodium chloride, there is a single molecule which will be divided or it will be dissociated and give rise to the 2 sodium ion and 1 chloride ion. Right? So sodium plus and Cl minus. Right? So the entire 1 molecules will be dissociated and produces the 2 ions. So that is sodium ions and a chloride ions. Right? So in such cases, what will happen? This results will be increasing in the number of particles in the solution. If number of particles which is increases means obviously the colligative property will be increases because the colligative property which mainly depends only on the number of particles instead of the nature. Remember? So that is why this is an example for the dissociations of the solute molecules or the solute particles. So understood what is the abnormal molar masses means? Remember what we have calculated the molar mass by using a colligative property, that values always it will be lower or higher than the normal value. So why this abnormality will be found? Only because the associations or the dissociations in the molecules will be taking place. So what is that association and dissociation? We all know that in a certain solutes, it will undergo associations, which means to say that the 2 acetic acid molecules will be undergo dimerizations because of the hydrogen bonding between the 2 acetic acid molecule. Because of the dimerizations, the acetic acid molecules will behave like 2 molecules of the acetic acids. So because of the associations between the molecules, it always decreases the number of particles. If the number of particles in the solution, if it is decreases means obviously the calculated value in the properties, the colligative properties will be decreases because of the associations of the molecule. Whereas in the dissociation, remember, dissociation means the single molecules will be dissociated and give rise to the ions. The best example is sodium chloride. It will be undergo dissociation and give rise to the 2 ions, that is sodium ion and a chloride ion, right? So because of the dissociation, what will happen? The number of molecules will be increased or number of particles will be increased. If number of particles increases means obviously what will happen? The colligative property will be increased. So this is known as abnormal molar masses. Hope you all understood with this topic. So that is why later, one of the scientists called as Vanta in 1886, he introduced a new term that is known as height. That is also known as Vanta Factors. That is also known as Vanta Factors, which is expresses the extent of associations and dissociations of the solute in a solution. In order to find about the extent of associations and the dissociations in a solutions, we use the Vanta factor, and it is introduced by the Vanta in the year 1886. So the Vanta factor is a ratio of a normal molecular mass divided by abnormal molecular mass. So Vanta factor, which is nothing but it is the ratio of the normal molecular mass divided by absorbed molecular mass. So this idea was given by the Vanta in the year 1886. So as we come to know that there is a lot of abnormality which we found in the molar mass of the solute as we calculated in the qualitative property. So later, in order to find about this abnormality, Vanta, he introduced a term known as Vanta factor, that is I, to find about that abnormality in a molecular mass. That can be find about by number of the normal molecular mass divided by absorbed molecular mass. The differences between these two which shows the abnormality. And it is also given by absorbed colligative property divided by calculated colligative property. Consequently, we can introduce the Vanta factors to modify the equations of the colligative property. So, for the relative lowering of vapor pressure, we can write the entire equation into I, because in order to find about the extent of associations and dissociations in the solid particles which is found in the solution. So, they have introduced the I, which is a Vanta factor. Similarly, we can introduce for the elevation in boiling point also the final equation, which is this one. So, which gives rise to the elevation in boiling point, which is multiplied with the I in order to know the association and dissociations of the solid particle. Similarly, in the depression freezing point also, entire equations will be multiplied with the I, and also in the osmotic pressure. This is how the Vanta, he showed the extent of associations and dissociations in the solid molecule by introducing the new factor called as I. Hope you are understood with this topic. Let's see the numerical, how to solve it from this chapter. Okay. Here I have taken the two numerical. The first one is the addition of 0.643 grams of compound to the 50 ml of a liquid, okay, whose density which is given, which lowers the freezing point from 5.51 degrees Celsius to 5.03 degrees Celsius. Calculate the molar mass of the compound, and Kf of the benzene will be given. So, from the formula only, from the numericals only, they have given the informations about to calculate the freezing point of the solution. So, we all know that how to calculate the freezing point of the solution, or a freezing point by using the molar masses. So, if you know the freezing point of the solution, we can easily calculate the molar mass of the solute. So, that can be calculated by MB, which is equal to Kf, which is nothing but a freezing point, that is a proportionality constant, into WB, which is nothing but the mass of the solute, into 1000 divided by delta TF, that is the difference in the freezing point, okay, into WA, that is nothing but a mass of the solvent, okay, which is given by WA, which is equal to, what is the mass of the compound, which is given to be 50 ml. The mass of the solvent will be 50 ml into 8 this is not a dash, it is 0.879. So, which is given in the density, right? So, 50 into 0.879, which gives us to 43.95 gram. So, because the mass will be equal to volume into D. According to the mass, we know that mass, which is nothing but a volume into D, that is nothing but a volume into density. That is why I have multiplied the volume into density value. Now we know the values for the VA, right? That is nothing but a mass of the solvent. In order to calculate the TF, That is a difference in the freezing point. How we can calculate? We know that TF, which is nothing but a TF naught minus TF. So they have given the values of this two, that is decreasing in the temperature from 5.51 to 5.03. So if you minus these two value, you will get the delta TF value, that is difference in the freezing point of the solution. Okay, that is 0.483. Now you know the values of the TF and you know the values of VA, that is WA, not VA, that is WA, and you know that the values of WB. So if you substitute the values in the above equation, you will get 5.12, that is nothing but a mass of the Kf, that is the value for the Kf, okay, proportionality constant. 5.12 into 0.43, that is nothing but a WB, that is nothing but a mass of the solute. Here we calculate the mass of the solvent and already they have given the mass of the solute. So the Kf value, which is nothing but a 5.12 into 0.643 into 1000 divided by the delta TF value is 0.48 into WA, as we calculated now by multiplying the mass with the density, that is equal to 43.95. If you multiply and you will get, and if you divide, you will get 156.059 gram per mole. So this is how, by analyzing the given problem, we can solve the numerical. Remember, always they'll ask us to calculate the freezing point or with the elevation in boiling point or with the relative lowering of vapor pressure or with the osmotic pressure also. If they have given, remember the K value also they will give, and you must calculate the molar mass by using that final equation. Okay, this is how, if you solve the problem, you will get 3 marks, and it is very important for the examination point of view. Next, we will discuss with the another problem, that is a 1.4 gram of acetone dissolved in 100 grams of benzene to give a solution whose freezing point will be 277.12 Kelvin. Similarly, the pure benzene will be freezes at 278.4 Kelvin and 2.8 grams of the solute will be dissolved in 100 grams of the benzene to give a solution which will be freezes out with the 277.7 Kelvin. Calculate the molecular weight of the solute. We all know that how to calculate the freezing point of the solution by using the equation. By using the freezing point of the solution, we can calculate the molecular mass of the molar mass of the solute, right? So here they have not given the Kf value for the benzene, right? So that is why we have to alter this equation, the entire equation what you have written in the first numerical. If you alter it, if you want to find out the Kf, so the Kf will be comes outside. So that delta TF into WA into MB divided by WB into 100. So you can write here MB, which is equal to Kf into WB into 1000 divided by WA into TF, right? Into delta TF. This is actually a equation to carry out the entire numerical. But here they have not given the Kf value. That is why I'll take out the Kf outside. So this will be multiplied with the MB. So you'll get delta TF into VA into MB, WA into MB divided by WB into 1000. Okay, remaining one. After this, we know that delta TF value can be easily calculated by this equation. That is, delta TF can be obtained by TF naught minus TF, right? So that is 1.28 into WA they have given, that is 100 gram, into 58, that is a molecular mass of the solute B. So that can be calculated by taking the acetone. Okay. Next, divided by WB. So WB, which is given, that is 1.4 into 1000. So it gives rise to 5.3 Kelvin kilogram per mole. Next, in order to calculate the molecular mass of the solute or the molar mass of the solute, so we will use the same equation because now we know the Kf value, right? So as we calculated now. So if you substitute the Kf value to this equation, you will get 5.3 into 2.8 into 1000 divided by 0.64 into 100. So you will get 531.8 gram per mole. This is how, without giving Kf value also, we can calculate the molecular mass of the solute by rearranging the equation. So hope you are understood with the numerical. So in the next session, we are going to deal with the another next unit. By this, I have completed this unit, and whatever I have completed in my session, it is very, very important for the examination point of view, especially for the 2 marks and also for the 1 mark. Try to focus on it, and we will meet you in the next session. Till that, take care and be safe. Thank you.